Hi friends, this is Rashekar, a GET faculty for electrical machines. Today in this video, we are going to discuss about transformer on loaded condition. Let's see, this is my transformer. Primary winding given by rated supply and secondary winding connected to the load, The primary winding having N1 number of turns, secondary winding having N2 number of turns. In secondary winding, the current is called I2. Secondary, the current is I2. At no load condition, the current in the primary is I0 only. But when load connected, here the current increases to I1. Sir, how much increases? If this is no current, no load, if there is no load, no current, then I1 is equals to I0. But when the load connected in the secondary, here I2 current flows in the secondary. Due to this I2, here some current is flows. That current is taken as I2 dash. This I2 dash and I0, sum of these two is taken as I1. Here, this I2 dash is called, actually this is load. Due to load comes in the primary. That's why I2 dash is called as load component of primary current. This is called load component of primary current. If load 0, load component also 0. This is simply. At no load condition, the flux is phi naught. This is only due to I0 current flows through N1 number of turns. When load connected, some flux produced in the secondary. This is due to I2 current flows in the N2 number of turns. But when load connected, here some extra current added. Due to that, some extra flux produced. That is phi 2 dash is due to I2 dash current flows through N1 number of turns. I2 dash current flows through N1 number of turns, then it produces phi 2 dash of flux. See here, this phi 2 and phi 2 dashes are equal in magnitude but opposite in direction. Equal in magnitude but opposite in direction according to Lenz's law. Hence, these two gets cancelled out each other. Phi 2 and phi 2 dashes both are cancelled each other. Then the total flux phi is equals to, phi naught only. The total flux phi is equals to phi naught only. Under no load condition, phi naught only. At loaded condition also, phi naught only. No load or load, whatever the load, the flux is constant. Whatever the load, the flux is constant. That's why transformer is a constant flux device. Transformer is a constant flux device. This is conclusion here. And another small conclusion. Here, phi 2 and phi 2 dashes are equal in magnitude. Phi 2 and phi 2 dashes are equal in magnitude. Phi 2 is due to I2N2 and phi 2 dash is due to I2 dash N1. I want I2 dash. I2 dash is equals to I2 dash is equals to I2 multiplied with N2 upon N1. This N2 upon N1 is also written as transformation ratio K and I2. So I2 dash is equals to KI2. I2 dash is equals to KI2. This is very important. And another conclusion. See here, again I am taking this one. I2N2 is equals to I2 dash N1. I2 dash N1. Yes or no? So generally here I given you what I given you. I1 is the sum of I0 and I2 dash. But this I0 is very less than I2 dash. If I0 is neglected, I1 can be written as I2 dash. I1 is equals to I2 dash. Now tell me, substitute here. I2N2 is equals to I1N1. So N2 upon N1 is equals to I1 upon I2, that is equals to transformation ratio K we discussed earlier. Therefore, the transformation ratio is equals to E2 upon E1. From these two cross multiply. I1 E1 is equals to I2 E2. Therefore, transformer is a constant power device. Transformer is a constant power device. Transformer is a constant flux device. This is simply the transformer at loaded condition. Transformer at loaded condition, I1 is equals to I0 plus I2 dash. Is a vector sum, not arithmetic sum. Right? This is simply the transformer at loaded condition. Now, let's draw the vector diagrams for this loaded condition. See here, we know already. Here, the supply voltage V, and here the induced voltage E. Of course, here the flux phi. Yes or no? And we know here IW and here I mu. Sum of IW and I mu is taken as I0. Up to this, the transformer at no load condition. But when load is connected, I2 current flowing here. When load is connected, I2 current flowing here. Yes or no? So, tell me, where is my I2? For example, this is V1 and this is V2. Of course, here E1, but here I am taking minus E1 and here E2 and here E2. Here V1 minus E1 and here V2 and E2. Now tell me, where is my current I2? Where is my current? If it is purely resistive load, my I2 is in phase with V2. If it is purely inductive load, 90 degrees lagging. If it is purely capacitive load, 90 degrees leading. If it is simply lagging load, for example, lagging load, the load is at lagging condition. Lagging, right? So lagging, nothing but where is my current? The current should be in lagging. So here V2. So the current is lagging. This is my current I2. The angle between these two is the power factor angle phi 2. The power factor angle phi 2. And if it is I2, its opposite direction, the current is called I2 dash. It is I2, its opposite direction, 180 degrees, I2 dash. I2 dash plus I naught. The vector sum of I2 dash and I naught. Vector sum of I2 dash and I naught. The vector sum of I2 dash and I naught is equals to I1. The angle between V1 and I1, the angle between V1 and I1 is a phi 1, the angle phi 1, power factor angle phi 1 and the power factor angle phi 2. Of course, this angle is the no load angle phi naught. The angle between voltage and current, this current is phi naught. This is simply for lagging load, the vector diagram. Once see clearly. Here, if the current goes in this direction, if this I2 is slightly doing like this, nothing but the power factor angle decreases. Power factor angle decreases, nothing but the power factor increases. The power factor increases. If the power factor increases, nothing but lagging to the unity power factor. Lagging to the unity power factor. Yes or no? If the current, this vector is coming like this. If this is coming like this, nothing but phi 2 decreases. If phi 2 decreases, power factor increases. If power factor increases, nothing but from lagging load to unity power factor. Then what happened to I1? Or what happened to phi 1? They will ask you question. When this I2 is like this, then our I2 dash comes into like this. Nothing but when phi 2 decreases, automatically phi 1 also decreases. Yes or no? Because this is decreasing, then this is also decreases. Phi 1 decreases, nothing but the primary power factor also increases. The primary power factor also increases. Once see, here I am doing that one. Once see, here I am writing that one. Here V1 or minus E1, here V2 or E2, and here the flux phi. Of course, here I am taking IW and I mu. Sum of these two is taken as I naught, and the angle is phi naught. Up to this is at no load. I said you I2 is in this direction vector, nothing but the power factor from lagging to unity, nothing but, for example, unity power factor or pure resistive load. For pure resistive load, the current is I2 in phase with V2. This is my I2. What is my I2 dash? This is my I2 dash. This is my I2 dash. Exactly opposite direction. The sum of I2 dash and I naught. Sum of I2 dash and I naught is nothing but I1. This is the angle phi 1. Nothing but, see here, when the vector is like this, nothing but phi 2 decreases. Phi 2 decreases, nothing but power factor increases from lagging to unity power factor. As usually, phi 1 also decreases. Phi 1 also decreases, then the power factor increases, but not unity. But not unity. Yes or no? Therefore, if secondary power factor is unity, primary power factor is not unity. Primary power factor is not unity. It is in lagging only. Even though the secondary power factor is unity power factor, the primary power factor is not unity. The primary power factor is in lagging only. The primary power factor is in lagging only. This is not unity. This is for lagging load and this is for resistive load. For leading load, you have to draw the vector diagram and conclude this one also. For leading load, you have to draw the vector diagram and conclusion also. Right, see here. For leading load, once see again the vector is same, of course. Here this is V1 or minus E1 and next this is V2 or E2 and here I have a flux. Of course, here IW, here I mu. Sum of these two is taken as I naught. And this power factor angle is no load power factor angle phi naught. Yes or no? No. Now see here. What is this? Leading load. Leading load, nothing but the current is leading to the E2 and this angle is phi 2. I want phi 2 dash, right? So this is a phi 2 dash, exactly opposite direction, I2 and I2 dash. Sum of I2 dash and I naught. Sum of I2 dash and I naught is equals to I1 and this is the angle phi 1. This is the angle phi 1. This is for leading load, the vector diagram. Leading load, the vector diagram. Again here, for example, this I2 vector in this direction. I2 vector in this direction, nothing but in secondary, if phi 2 decreases, nothing but in secondary, the power factor increases. In secondary, power factor increases, nothing but in secondary, from leading to the unity power factor. When it comes to from leading to the unity power factor, nothing but this I2 is here and then I2 dash is here. Yes or no? From leading to the unity. Yes, this is the leading, from leading to the unity. Then this I2 comes here, I2 dash comes here, and again the same vector diagram for unity power factor, leading to unity, lagging to unity. Wherever you go, you are going to unity. This is my unity power factor. So, if secondary power factor is unity, even though secondary power factor is unity, the primary power factor is lagging only, not unity power factor. It is lagging only. If this comes here, even though the primary is lagging only, nothing but in the secondary it may be lagging or leading or unity power factor, but in primary always lagging. Even though in the secondary either leading or lagging or unity power factor, in the primary it is always lagging power factor only. This is the vector diagram transformer at loaded condition. Very important. They may ask you conclusions on this. Are you okay? Right? Thank you. Thank you, sir.